All right, so we're going to talk about momentum and impulse now. I'm sure most of you have an idea of what momentum is, but we'll look at what impulse is as well. So momentum is really just inertia in motion. Now, what you think of as momentum is, wow, that really big truck has a lot of momentum. And so you think in your head, well, something that's really, really massive has a lot of momentum. But then if you see something going, like see a car zipping down the road, you're like, man, that car has a lot of momentum too. And it's all based on that speed. And so momentum deals with the idea of mass and speed. Since it's inertia in motion, a direct measure of inertia is mass. The more massive an object is, the more inertia it has. So, for example, if something is sitting still, then it has a lot of inertia to overcome to start moving. If it has a lot of mass and it's moving, then it has a lot of inertia to continue to move. Inertia, again, is not a force. It's just a property of matter. So momentum has to take into account mass and velocity. So mass and velocity. So the more massive it is, the more momentum it has, and the more velocity it has, the more momentum it has. Now, as an equation, momentum is P equals mv. P stands for momentum. No idea why. The only thing I can think of is we only have 26 letters of the alphabet. So they had to use something. M was already taken, capital M was already taken, so they just used P. So P is for momentum, M is of course for mass, and V is for velocity. So this is a vector quantity because it deals with direction. Velocity has a direction. The units are simply putting the units of these two pieces together. Mass is in kilograms, velocity is in meters per second, so the unit of momentum is a kilogram meter per second. So an object with momentum has both mass and velocity. If it's not moving, it does not have any momentum. It still has inertia, but it does not have momentum. So again, momentum is inertia in motion. The idea that an object in motion will stay in motion is the momentum. So let's do some practice problems. First one says, what is the momentum of a 10,000 kilogram truck moving at 25 meters per second? So first, let's underline what we're given. So 10,000 kilograms. Kilograms measures mass, moving at 25 meters per second. Meters per second measures velocity. And so we just take our equation, P equals mv. And so P is equal to mass, which is 10,000, times velocity, which is 25, and that gives us 25 with 4 zeros on the end. So 250,000 kilogram meter per second. What is the momentum of a 0.1 kilogram housefly moving at 1 meter per second? So again, we're going to use our equation. So this is our mass, because it's in kilograms. This is our velocity, because it's in meters per second. So 0.01 times 1 gives us 0.01 kilogram meter per second. And then what is your momentum? If your mass is 200 kilograms, so that's our M, you run with a velocity of 7 meters per second. So P equals 200 times 7, which gives you 1,400 kilogram meters per second. So how do we change momentum? Because a car is not going to drive at the same speed all of the time. We're going to have to change our speed. And so if we change our speed, change our velocity, then we're changing the momentum of the car. So to change momentum, you must change the mass or the velocity of the object. So you can either add or subtract mass to it, or you can change the speed of the object. So here's an example of changing the mass. So initially we start with a little car going 60 centimeters per second. So if we have a mass of 1 and a speed of 60, we have a momentum of 60 kilograms centimeters per second. But if we were to drop a brick into the car, the brick has a mass of 2. And so now we're adding mass, which means that the velocity is going to decrease. So since the velocity decreases, then we have a decrease in momentum here and an increase in momentum here, since the brick was actually starting at 0. So it starts at 0, ends at 40. This one starts at a momentum of 60, ends at a momentum of 20. Now what I want you to notice, it starts 60 and 0 for a total of 60. It ends at 20 and 40 for a total of 60. So momentum is changing between the objects, but the total momentum in the system is remaining constant. So changing momentum of the objects, but total momentum stays constant. So we'll talk more about that conservation of momentum when we get to collisions. So changing momentum means you have to change mass and or velocity. So we talked about changing mass. So now let's talk about changing velocity. So if you change the velocity of an object, that means it is accelerating. So change in velocity is defined as acceleration. It's change in velocity over time. In order to produce an acceleration, so to have an acceleration, you have to have a force. That was Newton's second law, F equals ma. So to have an acceleration, there has to be a force. So to change the momentum by changing the velocity, you have to apply a force. So a force must be applied to change momentum when dealing with velocity. So one way you can change the velocity is applying a large force over a short period of time. That would be your typical car crashes. So what you'll notice is this is in slow motion, okay? And in slow motion, you know that car crashes happen in an instant. And so you see that a force is applied by this wall on this car. So a large force stops the car. The car was initially going a certain speed. Now it's stopped. That's a change in velocity, a change in momentum. And we apply a large force in a short period of time. The other way you can do it is by changing the velocity, or change the velocity by applying a small force over a long period of time. So here is a large force over a short period of time, and now we can apply a small force over a long period of time. So one example is a runaway truck ramp. I have a video of this that I'm going to click over to in just a second, where it actually shows how the runaway truck ramp stops a truck. Over here we have airbags. Airbags were designed and created to help apply a smaller force whenever a person gets into a car crash. And we'll see how those work as well. All right, so this was a truck test, a runaway truck test. And what you'll see is this truck is not going to hit brakes. So runaway truck ramps are designed to help with trucks that lose their brakes on really, really steep inclines. And so when the truck hits the sand slows the truck down. So brakes can get really, really hot if used too much, and especially if you have something that is extremely large, like a semi-truck, then those brakes can get a lot of wear. So sometimes on really steep slopes, you'll see runaway truck ramps. And so this truck, for example, may not be able to stop. It's not going up the ramp, it's going into the ramp. It's very loose sand, and so you can actually see all the sand being thrown up here. And so what's happening is the sand slows the truck down so that the truck can actually stop safely. Now, airbags are a different way of applying a small force over a large amount of time. So without an airbag, your head would actually potentially hit the steering wheel. Instead, it's hitting this big pillow type thing. If you've never seen an airbag deployed, this is slow motion as well. It's an instant. In an instant, that airbag is deployed. But what it does is it applies a small force over a large period of time because the head hits the pillow, this airbag, and it slows down over a longer period of time instead of the head hitting the steering wheel, which happens in a split second, applying a large force in that split second. So here's from an overview of seeing an airbag working. So you see it apply, and you see that his head hits the pillow or the airbag. It's not really a pillow, but it kind of works like one. But the idea is that you hit this airbag, and it applies a smaller force to your head over a longer period of time instead of hitting the steering wheel, which would apply a very large force in a small amount of time. So, what is this idea of impulse? So, impulse is change in momentum. Change in momentum. So, for identical masses, so if the mass does not change, that was our truck ramps, our airbags, and our car crashes. So, a force must be applied. Everyone agrees that a force was applied to the car when it hit the wall. Everyone agrees a force was applied to the truck to get it to stop. And everyone agrees that a force was applied to the dummy's head whenever it hit the airbag. What can change the force, because the change in momentum is set, but how you can change the force is by changing time. So the greater the impulse, the greater the change in momentum. So, or you could think of it the other way around. The greater the change in momentum, the greater the impulse must be to change that momentum. So impulse has to deal with force because you have to apply a force to change that velocity, and it deals with time. We're talking about over a long period of time or a short period of time. So impulse is force times time. It's denoted by capital I, and it's equal to force, which is F, times little t, which is time. The units are either the same as momentum, kilogram meter per second, or it's putting these two units together. Force is in newtons, time is in seconds. So a newton second. So a car has a momentum of 150 kilogram meters per second. If it receives an impulse of 100 newton seconds as it hits another car, what is its new momentum? Well, impulse is change in momentum. So it has this initial momentum of 150, and it receives an impulse of 100. Since it's hitting another car, we're going to assume it is decreasing the momentum. So if it starts at 150, feels a change of 100, then the new momentum would be the difference between these two, 150 minus 100, which would be 50 kilogram meters per second. So it would have a new momentum of 50 kilogram meters per second. So as momentum increases, a greater impulse is required to stop. So think about if you're in a car crash when the car is going 20 miles an hour versus going 70 miles an hour. The 70-mile-an-hour car has a much greater momentum, so to stop it requires a greater impulse, a greater change in that momentum. If you are bringing a delicate object to a stop, so say your body in a car crash, and need to apply a large impulse. So you have an accident on the interstate. So you're going 65 miles an hour and you hit a car, which means you go from 65 to 0. So a large impulse. How can you minimize the force felt by the object? Well, impulse deals with force. It also deals with time. And so if you have a large impulse, but you need a small force, then you have to apply a large amount of time. That's what those airbags are there to do. That's what the seat belts are there to do as well, is to help increase the time in a car crash that you are experiencing to make sure that there is a smaller force that you are experiencing. So why don't we do some examples dealing with impulse. So we're going to start with the idea of momentum again, because it's change in momentum. So a 1,000 kilogram car moves at a velocity of 60 meters per second. What is the car's momentum? So we start with our momentum equation, mv. This is in kilograms, so it's our mass. This is in meters per second, so that's our v. And so we get a momentum of 1,000 times 60, which gives us 60,000 kilogram meter per second. So now it says how much force would be required to stop the car in 0.1 seconds. So this is our initial momentum. So initial momentum. Stopping is our final momentum. So final momentum is 0. If it's stopped, then our velocity is 0. So if we go from 60,000 to 0, then our change in momentum, or our impulse, is going to be 60,000. So if impulse is 60,000, impulse is equal to force times time. And so we get 60,000 equals force times 0.01 seconds, and we get a force of 6 million newtons. So this would be kind of a force that potentially the car would experience in that split second. So now, what if we had larger crumple zones in the car or something like that, and we're able to extend it to a full second? Well, we have the same initial and final momentum, so our impulse is still the same at 60,000. Oh, there we go, 60,000. And now the force is going to be exerted over a full second. So the force here is going to be 60,000. So we go from 6 million newtons to 60,000 newtons by extending that time. So you can see that force decreases as the time increases. That's an inverse relationship. So another example, this is kind of a factor problem because you see changes by a half. So this does not have any units, so this is a factor problem. So a car has a certain momentum and stops. So we're looking at a starting momentum and an ending momentum of 0 that are not changing. So our impulse is constant. We start with a certain momentum, we end at 0. That's not changing. But if we wanted to change the force by a half, how would the time have to change? So if we start with our equation here, I equals Ft, we're changing the force and we're changing the time. Impulse is not changing, so that goes away. Anytime you don't have anything left, you put in a placeholder of 1. The force is changing by a half, so let's put in 0.5 times t. So to figure out how the time changes, we need to divide by 0.5, and we get a time of 2. So if you want to half the force, you have to double the time. This is an inverse. This is an inverse relationship.